Thank you, Jennifer. Our next speaker is Dr. Wei Liao. He is a professional engineer and a professor and is the director of the Anaerobic Digestion Research and Education Center in the Department of Biosystems and Agricultural Engineering at Michigan State University. His group and the center focus on studying integration of solar, biological, and nanotechnologies for waste treatment and value-added fuels, chemical production. He also works on algae cultivation to reclaim water streams and generation of value-added products, as well as innovative anaerobic cultivation systems to convert organic residues into renewable energy and other bioproducts. And with that, I'll turn the session over to Dr. Liao.
Thank you, Brian. So let me start sharing screen. Okay, and yeah, our previous presenters, Chad and Nick and Dave, covered quite a bit in this entire anaerobic digestion principles and the other perspectives. And what I'm going to present today is actually we dive in a little bit into the details of the anaerobic digestion operations, very much some techno-economic analysis, life cycle, and from a long-term the operation at MSU. Again, we are the universities. We are willing to share those data and to actually very much is on the approach. How could we do that? And regarding the operation and regarding the economic and life cycle analysis, and I probably could answer some questions previous audience have. The digestive handling, those things we are intensively doing research at MSU ADREC, and I think next month I have another talk for the small scale digestion systems, and we'll emphasize a little bit more on both carbon and the nutrient streams. But this ones we are going to focus on carbon. Then I'll mention a little bit towards the end about the nutrient and liquid stuff. So the entire teams and our actually we're going to focus not just on the Anaerobic Digestion Research Education Center. We have another team actually under the Anaerobic Digestion Research Education Center, focusing on our actually called the demonstration digestion operation on campus. So the for me is the grad students actually working on this topic, put everything together, and Lou is the operator. And for our campus digester, then I, then as my colleague, we work together to actually doing anaerobic digestion research education, the matters at MSU. And we work with quite a bit of people in Chad before on the trying to kind of promote the digestion technology in the state and across the nation. So, okay, let's kind of move on. Actually, for this, the presentation, I really show a lot of data here and the approach. And the six the parts I want to cover. First, to give you a little bit of introduction of MSU operation. I think this our digester is the first one on the university campus, and I think UC Davis and other universities and built that the past couple of years. And then we do gain a lot of the information, experience, and also data out of our operation. Start from 2013. We start operation 2010 from a plug flow. We do have different type of digesters on campus, but I'm gonna focus on our South Campus the anaerobic digester is a completely continuously mixed stirred tank reactor. And then talk a little bit about the organic. We select Chad mentioned about cold digestion. Our operation is a cold digestion operation, and we receive a lot different type of the waste stream, organic waste stream. We'll talk a bit more on that, and then just share with the audience about long-term operational data. And there's some operational matter I will mention. It's not a kind of like you receive the waste dumping. It's not like that way. There's the steps actually we established at ADREC to investigate those feedstock and understand those feedstock and do the digestion afterwards. So then kind of get into the main piece, techno-economic analysis of digestion operation and the life cycle impact analysis of the digestion. And from those analysis, we will find out the current economic performance of let's see the typical digester system. And then, of course, from life cycle impact assessment, we see those carbon credit and then the nutrient aspect. How could we move your digestion technology towards the next, the level, next generations? Then kind of give you a little bit summary. So a bit of background on the MSU campus digesters. Actually, it starts from our campus sustainability plan. And MSU do have a plan to achieve the green campus, we call green campus initiative. And MSU is pretty big university. We have 50,000 students on campus, and we have 12 cafeterias around campus. And then because our college of agriculture, we have all those animal farms, dairy farms, swine farms, chicken farms, horse farms, and all those farms generate the waste stream. So the rationale to build our demonstration projects from this part, we want to handle waste stream before we build our digesters. All those wastes are going to landfill, which is not a good way to handle them. They're organic matter. On the other end, at the same time, we established the Anaerobic Digestion Research Education Center, at MSU. We run the in-depth. We do both fundamental and applied research related with anaerobic digestion. Start from the microbials, metagenomic, the things, twist a little bit about the microbial to improve their performance, to enhance gas production or some other matter handling different type of waste streams. And of course, system integration. We do consider the anaerobic digestion technology is a cornerstone for big systems, incorporated with solar. Like right now, we're doing a lot of the solar bioconnect research for different agencies, the DoD for those places, and then of course the anaerobic digestion is a hub process. I have to see that it's very good at carbon capturing and sequestration. However, nutrient is not, and phosphor, ammonia after digestion you have pretty high concentration digestate. And in state of Michigan, they're trying to put the newer regulations right now to limit those digestate discharging. So there's kind of some the discussion on that part. So I think around the country, sooner or later you'll see more regulations on the digestate, and particularly on agriculture part. And Nick mentioned a little bit in the EPA, but I think EPA is aware of that, and then we need to come up with a solution from technology standpoint. We need to develop technology and economic feasible technology to address wastewater, address this liquid digestive issue, extract phosphorus, nitrogen, those things. And that part is we're going to talk about the next time, but this kind of our research emphasize on that. And of course, our demonstration, we want our the campus digester renewable electricity is one of them. We want to kind of generate like renewable electricity at current moment. And our electricity power 10 buildings on southern campus, including my center. Actually, the ADREC center is 100% powered by our own electricity. Then, of course, some other factors in terms of from the research standpoint of view, climate change, the greenhouse gas emission, and those kind of stuff. So that's kind of rationale. So we want to build again as a researcher in the university to go that route to build a large system on campus research. Really back then was a very, very big decision because it's very much kind of out of the regular research themes, and we do the pilot systems on campus too, but reach to that large demonstration systems is a different. So, but we're glad we made decision back then to build the system. We did gain a lot of the information. We did gain a lot of the experience out of that. So this is where the MSU Southern Campus anaerobic digester is actually next to the MSU dairy farm on the Southern Campus. We build the systems behind MSU dairy farm, and this is the MSU anaerobic digestion research education center. Is a 6,000 square foot building, and we do a lot of anaerobic digestion related research there. We have pilot system in there, and high bay area can do some sort of fabrication and manufacturing there. And some of you may know we are getting some of the state funding. This dairy farm is fairly old, 1964, and there's some issues and related with the facility. Actually, MSU is going to build a new dairy farm, 700 dairy cow system just on the southern part of the current dairy farm. And we are going to expand a little bit our dairy operation, our digestion operation to handle the increased the amount of the waste. So current systems right here, we have actually two systems. One is the plug flow, the 250,000 gallons the plug flow systems, and 500,000 gallons of CSTR systems. 250,000 gallons plug flow is not running. That's actually related with nutrients handling. The MS is a pretty big campus. We have 5,000 acre lands, the farmland. Actually, we dump our the digestate as a nutrients on those land. But if we turn both systems on, and our land's not enough to handle particular phosphorus from the digestate. So right now we're just running the CSTR, the 500,000 gallon systems. So then this is kind of some of the data related with our systems. Again, digest tanks 400,000 gallons effective volume. The entire volume is actually 500,000 gallons. And the size of the digester, we have two of them. Actually, the fermenter is just one of them. And the green tank is storage. Again, the EPA regulation cannot dump those digestate on the field during winter time. So this is the 2.1 million gallons storage tank just for the digestate. After the anaerobic digestion, we do the liquid solid separation. All liquid digestate the stored in the green tank, and then during summer we apply them on MSU farmland. And then we do have the CHP unit 400 kilowatt electricity generation, and we do recover the 450 kilowatt equivalent thermal energy to maintain temperature of the reactor. Actually, the entire systems really need a little bit energy from the biogas. Actually, we send all the thermal energy to heat the building. We do have another 3,000 square feet the building next to the facility. We heat the building and then send some other heat to the other users. And then the digestate treatment, we do have a press compressor separator, separate liquid part and solid part. Liquid part, again, as mentioned earlier, back into this tank stored there. And solid part, MSU, we do have the composting facility. And all those are solid, we compost them. And then during the springtime, actually used for the landscape and over in the capital city, East Lansing here, and then also we actually sell them to the general public, the yard based, and then the rest of the compost we applied on our land as the fertilizer, as soil management. So this is a whole the flow chart, our system. And again, this is a demonstration / research unit. We do take samples, and we monitor the systems very carefully. And we do have two piece, food waste piece and the manure receiving piece. And then we have a mixing tank. We put this, the two streams mixed together. And then we do have a small grinder there, and to particular for food waste. Sometimes those tomato and those stuff in there, we need to kind of grind them. And we're sending to our the main fermenter, digester, generate methane, and then after that, the digestate, we do the liquid solid separation, and the liquid we store in our holding tank for the land application, and then the solid part just for the composting, and then the biogas for the both tank, actually digester and holding tank. Actually on the top, you see the pictures. The dorm actually gas store in the dorm, and then we take gas out from the dorm, and we do have the active carbon unit to remove the hydrogen sulfate and dry a little bit the gas before sending to the generator to generate the energy. And those yellow boxes is a sample we take. And because we have a labs next to the digestive system, we do intensive measurement on those, monitor the whole system. This is why we generate later. You see all the data we have. So that's kind of the process flow chart for our system. And then kind of jumping to the waste streams that we're handling. Roughly, we handle the 8 to 12 different type of the waste streams. And manure part, we do have the dairy and the chicken and the liver swine manure and into the systems. And the food waste is very much on the pre-consumer and the post-consumer food waste. But recently, I think, Chad, you probably run into the same thing for your digester. A lot of requests for the fogs and the fat, oil, and grease. Currently, we dump a lot of fogs into our digestion system. However, that's a very critical and very tricky part, and the carbonation ratios, because fog carries a lot. Fog is good, however, it dump too much into the digestion system, it could cause the failure of the digestion operation. So we monitor that things very carefully, and based on their carbon natural ratio, and also based on the fatty acid concentration. And we have a different system that dump, the dump those waste into, our the systems, and some of from cafeteria, they come in carts, and we do have tipper dump into the piece, and large, the dining hall, like on campus, Brody, those, dining hall, they do have their pump machine, and they send in container, dump into systems, and this is a kind of a truck, and the bring the fog to the our system, and then some other, fruit, vegetable, a pretty big piece. So we do need, a shredder or grinder to reduce the size before pumping our systems. So this is all kinds of, see the very diverse, the feedstock streams we have. So just from fat to food to pineapple peels. And one time in Michigan, because of the egg issues, the entire cart of the eggs, we just dump into our systems. We handle those things in two pieces, manure piece and food piece. And then we record all the data. So we have this splatter, the chart, and for each categories of the waste streams we handle, like we track them based on monthly base, 12 months, and we make those can chart. And this presentation, just because of this new system, we start 2013, so we collect all the data from 2013 till now. But presentation just the end at 2020. You can see the food piece and manure. We actually feed around 47% of our total, the feed digesters actually from the food waste. So it's a large, portion of the food waste. I remember somebody asking us about, the renumbers, in terms of, cold digestion or biogas from cold digestion. That's very tricky because that much of food waste is hard for you to clean renumber. Renumber is based on the particular D3. It's based on the cellulosic base. Manure could be, but food waste is a bit tricky. So that's something I think probably Nick can answer a little bit more question from an EPA standpoint of view, the regulation, those things. So this is kind of our, the organic waste, and we do run detailed characteristics of, those feedstock, like our polymer manure from the dairy farm and the beef. We have some beef manure there too, and those different, things. I'm not going to jump in the detail, but we do the total solid, water solid, pH, the electric conductivity, and the soluble COD, TNTP, ammonia. So then we do monitor, because we do have online systems, all the temperature, those things. We maintain our digest temperature around 40 degrees C. And then you can see that we record the highest temperature and the lowest temperature actually on daily basis, but just kind of give you the profile, the average, the temperature profiles here. So you see that digestion operation temperature maintain pretty good temperature around 40 degrees C, a little bit higher than the mesophilic 35 degrees C requirement. Again, this is our consideration to want such a big tank. Temperature, if it varies, very hard to bring temperature up. So we're trying to maintain the temperature a little bit higher than the required 35 degrees C. That I think is most of digestion operations in the around country is probably doing the same things like ours. And then the HRT, we do kind of record based on feeding and do the calculation. Our HRT is between 20 to 25 days. There's kind of some occasion the feedings. Again, this is an agriculture operation. It's quite a stable, but if you look at a daily basis, again, big variation. But sometimes we get like 30 days retention time. But average is around 25, 26 day retention time, hydraulic retention time for our digestion operation. And then we do the collect data. We run the statistical analysis, and this is the daily base, gas production for every year. And this volume chart show us a couple of information. One is kind of mean value and the distribution of gas production. You see the kind of tail, those things. and a normal distribution, and then the kind of extreme values, lowest value and highest values, all in this in the chart. You can see the first couple of years we start operations 2014 and a little bit bumpy up and down, and then after actually we gain a lot of experience, control the feedstock and based on their carbon nitrogen ratio, and then adjust temperature and other operational matters. And start 2017, the operation is pretty stable in terms of gas production, even though still some of the outliers during maintenance, and again, oil change, those things we do need a maintenance. And then the electricity generations are pretty stable out of our systems. This annual base 7,500 kilowatt on our average, a daily basis energy production. You will see some numbers later on. And then again, the H2S concentration monitor that we do have online measurement there, and again between average is around the 500 the ppms, and we do need to remove them before sending to the generator. And the methane content is right around 65%. Recently, a bit higher because we add a little bit more carbon stream into that. We go to up to 70%, but the average is around the 65% of your methane content, volume based. And then we monitor the total solids in the digest state before the sent to the liquid solid separation. We do monitor all those total solids pumping to the systems, and nitrogen too, phosphor, and pH. Again, pH is as Chad earlier mentioned, pH is, I think it's simple, in the simplest, easiest way to actually give you first-hand information how healthy your digestion is. So for that case, if you can maintain about 7.5, your digestion is okay, doing fine. And if you're dropping quickly down to 6 point something, below 7, then there are some of the issues. You do need some red flag. You need some considering the feeds you feed into the systems, probably too much carbon, those kind of stuff. And then the TS/VS reduction, again, our system, we have roughly around the 43% total solids. Again, the particular mixed streams from Manure, there's some of, our dairy farm is, is organic bedding. It's not sand bedding, but still there's something in there and influence, total solid reduction. But total solid reduction is around 48%. It's a typical numbers for agriculture digestion system. And this is a kind of summary for our operation, really trying to kind of lump everything together for past the 8-9 years operation. And I can see that our input, the average, so based on yearly average, roughly feed 22,000 metric tons the waste into our system. Literally the split half from the agriculture, Manure, half from the food waste, and then we generate annual base, the 2.67 million kilowatt hours electricity. And then the effluent was separate. We have the wet fiber because we record them is because they are used for composting. We do need a meter to need a know the amount of the wet fiber sent to our composting facility. So okay, then kind of with all those the operational data, then we come to we want to summarize. We want to do techno-economic analysis and the life cycle analysis. So we have actually two aspects on that. We at ADREC, we do a lot of feasibility study for different company farms around the country, around the world. Actually, we do something for Latin America too, and that's for the feasibility study. We gain certain a number, put our experience on. We run those analysis, show them payback period and some other information they need to know. But for this, techno-economic analysis and life cycle analysis, actually back end, we get all our data, we put them together, and really look into the real performance of our system. So what do we do? This should show you approach, and we have a lot of data in this presentation. Cannot show all those data, and we run mass balance first because we record all the data, annual base and mass balance, and this is the average between 2018 2020. But we do run that every year. The mass balance, feedstock, amount of feedstock, and characteristics of feedstock, and methane gas biogas production with different composition. Methane, carbon dioxide, effluent, and wet digest state, the filtrate, all those numbers, we keep tracking on that because we do need a mass balance and to run next steps, all the techno-economic analysis thing. So build up on mass balance, again, we record energy consumption, energy generation. So we run another detailed energy balance for that case. And if you look at that, we meter everything. So if you look at heat input, electricity input to maintain digestion operation, and look at all the energy output from the biogas production, roughly our systems in the Michigan winter is pretty cold. So, and we roughly use 10% of total the biogas energy to maintaining operation, pumps, the heating systems, and then all those things. So which means like an agricultural digestion system, we do have a pretty good net the energy, the generation. 90% of the biogas energy could be the revenue used for renewable natural gas, and we talk about later on, and then the electricity, some of those kind of even kind of use messing as a chemicals to produce some other feed stuff. So this energy balance build up on the mass energy balance, then incorporating with the other parameters, the capital investment, operational investment, and then we can run a TA, techno-economic analysis. So roughly this is our investment. Our systems back then, 2013, we put $3.5 million to build a system. And of course, the digesters is a big component. And actually, I have to emphasize on it because we have two tanks. That 2.1 million gallons of holding tank, we spend quite a bit of money. It's very large, right? This is why current our research very much focus on digestate treatment. We want to develop economic, feasible solutions that actually can treat liquid digestate right away, and then can reach to at least discharging standard, either kind of linked to your municipal wastewater treatment plant operation, and we can handle that, or can we reach to high quantity, we can direct discharge. Then we can actually reduce this digestion cost by half, and actually really kind of save quite a bit of money there. And other part is I have to say the electricity part. I think we have somebody from the consulting company that have been doing the paperwork. Those interconnections is really hassle. I can tell you, Chad is here too. And let's talk to those utility companies, right? And interconnection, particularly the volumes is matters. Actually, if you have like a megawatt or a couple megawatt, the production probably putting you a little bit good shape. And but for those small, medium, the agriculture operation, it's hard to try to do those kind of stuff. So, but yeah, of course, the MSU, we do talk to the end consumer energy, and then we do have our campus utility power plants. We actually send all those utility, the electricity to our campus grid. Then also, of course, site improvement excavation depends on where you are, and if you own your lands, probably can save some money on that part. And operation. Yes, another very big piece. Maintenance is not trivial, and particularly have a generator there, and oil change, all those things costing money. Of course, the labor. We do have our dedicated technician, one full-time person in charge of that, with some helps from students, from on-call employee, and then those the money, put them together, and the revenue. We do have two streams. Now, like most of agriculture digesters, electricity for sure, we sell electricity, but electricity is not, I have to mention that, in the state of Michigan, and there are some years we only sell electricity at 6 cents per kilowatt hour, and good years for 10, 12 cents, and I think this recently we got a little bit getting the price, but 10 to 12 cents still not going to make you a very good economic the case to let the people to implement that. So this is why we have another streams. It's tipping, and depends on different customers. We do have a different contract, and they pay different fees. And to ours, you can see the tipping and the revenues. These two the pieces for our overall revenue. And based on these two the streams, our payback period is 21.5 years. 21.5 years is just too long for commercial operation. 100% sure. And for our university operation, because we're doing considering this as a research the activity, so then probably okay for that case. But to improve the payback periods, to improve economic performance is critical for digestion operation. This is why in California, because they're moving to renewable natural gas, and that kind of Nick mentioned in his presentations, growing that part, because yes, the revenue from the renewable natural gas is much, much higher than electricity. However, again, the scale does matter, as mentioned earlier. Those, large farm operation, large operation, they can go for renewable. How about the smaller ones? If you just look at dairy industry, 90% of farms are small, medium farms, which means that you have less than the 1,000 dairy cows. Most of them like 100, 200 dairy cows. Very hard to implement this technology. This is why we do need a package of solutions. Renewable natural gas could be one. Right now, so actually MSU are very much involved in the electric vehicles. So those electricity for small dairy farms, if we can turn those electricity to for the EV charging, that's another story. That's why the E-ring, keep on the E-ring, a lot of rumors, as Dave mentioned there, and we really don't know what the E-rings look like. Hopefully, those the regulation or the policy out will benefit for the digestion technology to be implemented in small medium operation. So that's just kind of, we can talk later on regarding this, our techno-economic analysis. And we do it on the sensitivity analysis, you can see the for sure revenue, right? Back-end electricity, the cost. If we can increase 25, this calculation based on 10 cents per kilowatt hour selling price for electricity. If I increase 25% of that selling price, actually the payback period reduced to less than 10 years, around 10 years. 11 years payback period could be reduced. 10 years. 10 years is much better than 21 years. And this is kind of, revenue streams. So something we need to really focus on. And no matter renewable natural gas or the electricity for EV, and we do need a package solutions to help the agriculture side. And municipal is a different story, but same thing. And if you increase revenue stream, will help municipal side as well. And then kind of quickly goes through the life cycle, the assessment part. And again, we compare with conventional operations like landfill and lagoon storage for those agricultural waste streams. And landfill is for pretty much for full waste. If you have the solid full waste, very much is going to landfill, but manure is we store in the big lagoon, most of agricultural operation. And compared to our the cow digestion systems, we call that scenario 1, scenario 0. And actually, so the life cycle is very detailed. You need to build the inventory. It's literally, it's like a big mass balance analysis. Every single atom in there related to carbon, because we focus on two, the impacting and potentials. One is the greenhouse gas emission, very important. The greenhouse gas potential. The other one is water eutrophication potential. Water eutrophication potential is very much on the nutrient part, phosphorus, nitrogen. And a global warming potential is very much on the carbon side, methane, carbon dioxide emission, and the nitrous oxide emission too. So I'm not going to do detail on this table. That's just a typical process. If you run life cycle, you do need to have an inventory. And based on inventory, based on EPA's, the Tracy numbers, and we do all this kind of calculation. And this again, this inventory. And I just want to show a little bit of numbers. These two figures, very important figures I want to show you. One is like, so as mentioned earlier, anaerobic digestion is a very good carbon capturing process. And you can see that, they compare to the land application, landfill, and then the manure lagoons, because we do handle food waste and manure, we have to consider both of them. And I can see the digestion operation. The digestion operation can reduce global warming potential by 70%. Because collect methane and also replace some of the fossil-based electricity. This is renewable electricity. However, if you look at nutrients, water eutrophication potential, yes, we do contain them, and we do the reduce some of the nutrient release, and then because we change the format of phosphorus and the nitrogen, and we do collect solid digestate to actually do the composting, right? And only digestion process only reduce the water eutrophication potential by 25%, which means, as I mentioned earlier, digestion process is more like a hot process, very good at carbon. And in terms of phosphorus, nitrogen, and a lot of people say, okay, liquid digestate is a good fertilizer, but if you, I think many of you ours, and many of you in the audience, if you're from farm side, you will tell me how difficult to handle those liquid digestate as a fertilizer, and you need to watch a lot of things and a lot of the work, labor's involvement to do that. So our current potential for the liquid parts, we do need to extract both phosphorus and ammonia into at least a semi-solid form, and you can apply them. and you can easily transport them and get clean water. And clean water, I'm not saying the drinking water, but even though we're doing research on that part, but the discharging water, satisfied discharging standard, we can kind of discharge water to to a surface water to the ground. So that's kind of just based on this life cycle analysis, it gives us a very clear direction. And for in terms of the anaerobic digestion technology, what's the next steps? Of course, implement those treatment technology always need some of the money, capital, and operational. Where are those money coming from? Actually, the systems. That's why I talk about carbon in the front end. If we can increase revenue from the carbon source, renewable natural gas for large operation, and that's for small medium operations. This is why we do a lot of research on that. Electric vehicle charging. If you look at the numbers of the EVs in the next 5 or 10 years, it's going to be huge. And rural area, we don't have it. If based on DOE numbers, right now, every day increase. Right now, we have like a 46 or 47,000 charging stations around the country, very much is on the highway and big cities. And a rural area, we don't have a lot. And for the commercial charging stations. And we really, this is an opportunity for us. I think if Nick's here, I think we can chat about that things. We're doing those things with USDA, ARS, and we're working together, trying to get some of some sense regarding that agriculture digesters and the EV charging. We do have a state projects going on right now. We build some pilot systems to verify the whole concept. But again, this is what I mentioned. If you can generate revenue from the carbon side, then we use that revenue to support and the nutrients for digestive handling. That kind of makes the whole the loops closed and actually making us move the digestion technology to next level. So that's kind of the bottom of talk, and I know that it's kind of close to launch. So this is just what I mentioned in the presentation, and the multi-waste streams is the way to go if you want to increase methane production. But of course, if you're talking on green number, it's a bit tricky. And if you want to claim the cellulose-based the fuels, and you have to kind of stick with the manure. And then again, as mentioned, later on about the liquid digesters from life cycle, and then nice to see we do need technologies to handle phosphorus, nitrogen in the liquid streams. So, and this is again, this is our anaerobic digestion center. We run a lot of the things for different sectors and government agencies, companies, and we do the BMP test and we do feasibility study. And we have all kinds of the pilot system, container-based systems to the different tasks for the military, military base, and for small communities. And then we do have international the center hubs, like in Central America, Costa Rica. We do have the small pilot systems to run some of the waste handling for that part of the world. And yeah, that's about my presentation. Hopefully it gave at least some minutes so we can have some questions and answers. So thank you all.
Thank you, Dr. Liao. There are some questions in the chat, and we have a couple minutes yet to try to answer a couple of those.
Okay, I cannot see the chat. Okay.
I can read a couple of them for you.
Brian, can you I cannot focus on.
Yeah, that's okay.
Yeah.
Do you add any coagulants or flocculants to your effluent separator to achieve that 27% solids?
No, not at all.
Okay. Do you use any sugar beet pulp or organic waste from the sugar beet industry in Michigan?
Very small, not a whole lot, very small. Actually, that's a very good point. We are right now doing sugar beet, the research, the pulps, the residues, and not like a large quantity and small amount from the research side. We do dump into our the digestion system, but that amount is really tiny. It's not influencing big our performance.
The next one is being in a colder climate, how much do you notice the winter months changing production and affecting your ability for storage and managing temperature variations?
Actually, for the production is not influenced a lot, but operational, yes. And because our system is sitting on the wind chill, and winter times, particularly the frozen province, right? And that's pretty hard. for the energy mass balances kind of maintain the pretty routine. But we do need before winter comes to do installation. Even sometimes we need to protect a little bit our engine, build and put those the corn stover bales in front of the engine to do some protection. Yes, that's the operational matter. But in terms of the installation, temperature management, as you see the slides, we did a pretty good job. And of course, in wintertime, it consumes a little bit more energy to maintain the temperature. But overall, annual base, we only consume around 10% of our biogas energy to operate our system.
Another quick question was, research digesters have purification equipment necessary for RNG output?
Not right now. We don't have the RNG. RNG is part is like at a lab scale research. We take them at this moment. We don't. We do not have the RNG unit on campus.